Today we're going to talk about the exciting work that has been done to accelerate data science workflows on GPUs. We're going to begin by talking about gradient-boosted decision trees in general, and XGBoost in particular. Then we're going to move on to discuss its success in marquee prediction challenges and advantages this algorithm has over other approaches. We're going to talk about the rapid suite of open source software libraries and how to get started using them. And finally, we're going to walk through 3 examples involving a single GPU, multiple GPUs, and conclude by briefly discussing how to set up multiple nodes of multiple GPUs. There will be some time for questions at the close. XGBoost, originally introduced in 2014, is an implementation of gradient-boosted decision trees. The idea of gradient boosting, where stepwise additive expansion is based on a loss function, has been around for almost 20 years. But what makes XGBoost different from other similar approaches is that it was built to make optimal use of system resources and that certain improvements were made to the model itself, making it more robust and accurate in general. Early in 2018, a group of researchers from the University of Pennsylvania released a study comparing 13 leading machine learning algorithms for classification across 165 publicly available classification problem data sets in the field of bioinformatics. What the authors found, after they'd run more than 5 million various model specifications, is that gradient-boosted trees consistently outperformed the majority of algorithms in the majority of cases. The mean ranking of the algorithms across all data sets is displayed in the figure that you see here. Ranking is determined by the 10-fold cross-validated balanced accuracy of each algorithm on a given data set, with a lower ranking indicating higher accuracy. The rankings show the strength of ensemble-based tree algorithms in generating accurate models. The first, second, and fourth ranked algorithms belong to this class of algorithms. The authors also performed tests of statistical significance of the observed difference between the algorithms. According to the authors, the test, quote, underlies the impressive performance of gradient tree boosting, which significantly outperforms every algorithm except random forest at the 99% confidence level. Here we're going to walk through a simple example of how a gradient-boosted decision tree model is fit. Here we have a data set of 5 observations, and we have data about their age, gender, occupation, and whether they use a computer every day. We're trying to build a model that will predict if an individual likes computer games. The first model we build is 2 levels deep and divides the data into leaves based on 2 features, age and gender. Each observation is then given a prediction score. Now the algorithm creates another tree. This tree is only 1 level deep and splits the sample based on 1 feature, daily computer use. Like the last tree, the single tree assigns a prediction score to each observation. At the bottom of the slide, we can see that when we make a prediction now, we add the scores an observation is assigned by each individual tree. The criteria for building trees and the number of trees included in the model is controlled by hyperparameters decided on by the data scientist. I will discuss this a little bit further when I walk through the Hello World example that's included later in this presentation. This is a partial list of the data science contests that XGBoost has won when used on its own and not as part of a larger ensemble. I picked these examples to highlight the diverse types of problems the algorithm successfully tackles. The Kaggle contest in 2015 sponsored by the Caterpillar Company, asks contestants to predict the price a supplier will quote for a given assembly of machine parts needed to produce their heavy equipment. CERN asked Kaggle contestants to identify a rare particle decay phenomenon that helps establish proof for a new understanding of physics. The Association for Computing Machinery's KDD Cup 2016 challenge asked participants to create a ranking of academic institutions based on each institution's predicted future acceptance rate for papers submitted to conferences. The 2017 ACN Rexis Challenge asked participants to match job postings with candidates that were qualified for these job postings. Here we have 4 predictive success stories across highly disjoint problems. This illustrates that XGBoost is flexible enough to be applied in a wide variety of situations. This is one of the reasons why Rapids chose this algorithm as its first to accelerate with GPUs. I like to call XGBoost a desert island algorithm because if I had to pick just one to do all my work with, XGBoost would be it. What makes the accuracy of XGBoost all the more appealing is that it can be understood and explained to non-technical stakeholders. Despite the huge success that various neural net specifications have had in the past few years, being able to explain why the models made the decision that they did is an area of active research. In contrast, models estimated with XGBoost can be explained to non-technical stakeholders as easily as an ordinary least squares or logistic regression. The parameters are estimated to minimize prediction error, and the relative impact of each parameter can be recovered from the fit model. In many cases, even if a model is performing at a high level, if the data scientist can't explain it, the model won't or can't be used. XGBoost does not suffer from these problems. XGBoost in early iterations does have some limitations. Despite its speed compared to other similar algorithms, when problem sizes grow sufficiently large, training models can take a very long time. Almost every data scientist is familiar with waiting for a model to finish training, making small adjustments, and then waiting some more. For large problems, tuning hyperparameters can take days or weeks. CPU XGBoost relies on an approximate greedy algorithm for determining tree splits when the data set is too large to fit into memory. This can lead to a decrease in accuracy. For some prediction problems, this decrease in accuracy can actually be very costly to the business. With Rapids and XGBoost, data scientists are able to interact with their models in a more nimble way. Here we have a graph describing some benchmarks of GPU-accelerated XGBoost compared to CPU nodes of various sizes. The DGX2, which is for our purposes a single node of 16 GPUs, outperforms 100 CPU nodes substantially. 5 DGX1s, 5 nodes of 8 GPUs each, also substantially outperforms 100 CPU nodes. Setting aside the major engineering challenges of a 100-node cluster, we can see that you could run your model on either of these two configurations more than 10 times and still be done sooner than the first run on the 100 CPU node cluster. After hearing me mention it on the previous slide, you may be asking, what is Rapids? Rapids is a suite of open source data science tools accelerated to run on the GPU. Currently, Rapids consists of cuDF, a package for reading data to the GPU and interacting with it in a way similar to a Pandas data frame, QML, a package that contains common machine learning algorithms with an API similar to scikit-learn that have also been GPU accelerated, and cuGraph, a library implementing graph analytics functionalities based on GPU data frames. At Rapids.ai, there are a lot of resources for getting started. We provide documentation, data, and a few ways to begin working with Rapids, including containers on NGC and Docker Hub, as well as a way to install directly on your machine through Conda. Rapids is brand new, and Rapids development is very active, with new features being added regularly. In the near future, there will be a set of tools to create visualizations directly on the GPU. The vision for Rapids is complete end-to-end machine learning workflows that happen entirely on the GPU. This will allow data scientists to iterate more quickly, work on larger problems, and make better predictions, all in far less time than other alternatives. Additionally, as we'll see shortly, anyone that is currently working with the common Python data science tools will be able to jump right in and start coding. This means that accelerating your current workflows doesn't require learning a new API or substantial revisions to your existing code. Here I've listed the prerequisites for running Rapids, either directly on bare metal or in a Docker container. The prerequisites include a Pascal or newer GPU architecture, CUDA 9.2 or CUDA 10, and Ubuntu 16.04 or 18.04. To run the Rapids Docker container available on Docker Hub, you need Docker CE 18 or newer, and NVIDIA Docker 2 or newer. There are NVIDIA solutions for each part of the data science lifecycle, from early experimentation to large-scale data center applications. Early exploration can be enabled by our brand new Titan RTX. This is a powerful computing solution that anyone can acquire and begin seeing immediate results with. This is a great way to get started. As use cases become business critical and the problem sizes get larger, it's worth considering enterprise solutions like the Quadro workstation with two-way NVLink. An even more powerful solution to work with large data sets is the DGX station with four-way NVLink, which enables the shortest training times along with the largest memory footprint on a workstation. DGX1 with 8 GPUs and DGX2 with 16 GPUs provide even more power. DGX Station and the DGX 1 and 2 servers offer high memory bandwidth, supporting fast data movement between GPUs thanks to NVLink and NVSwitch. They're a single dense compute machine that enables easy scale up and out, backed by full stack enterprise-grade support from NVIDIA. A Rapids container is available on NGC, the NVIDIA GPU cloud. The NGC container registry provides researchers, data scientists, and developers with simple access to a comprehensive catalog of GPU-accelerated software. NGC features over 40 ready-to-run containers for machine learning, deep learning, and high-performance computing that take full advantage of NVIDIA GPUs on-premises and in the cloud. You can download the Rapids and any of the other optimized containers and run them on Amazon EC2, Google Cloud Platform, Microsoft Azure, Oracle Cloud Infrastructure, NVIDIA GGX systems, NGC-ready systems, and select Titan and Quadro GPUs. For bare metal installs, Rapids is available through Conda. Anaconda is a free package manager, environment manager, and Python distribution with a large collection of data science and other open source packages. It's also available in a more lightweight version known as Miniconda. Using Conda is the easiest way to install Rapids to your machine. Full instructions are available at the Rapids homepage, rapids.ai. Support for pip installation is planned for the future, but as of right now, it's not currently available. A Rapids container is also available on Docker Hub. These containers will be updated frequently, so check back every so often for updates. The container includes all the latest components of the Rapids project, as well as examples, and can be interacted with either via a Jupyter Notebook or from the command line. Here we show how you can get started with Rapids in 4 lines of code. First, pull the Docker container from Docker Hub. Then, run the container. In most cases, you'll also want to mount a volume containing the data that you're working on. In this example, we're starting up a multi-GPU instance of Rapids. The first port that we map is for the Jupyter Notebook. The second is for the Dask dashboard, which we will discuss later. The third is the Dask scheduler, which will handle the multi-GPU workload. The container includes a Python virtual environment. Once that is activated, the includer helper script to launch Jupyter can be run, and the Jupyter Notebook will be available for you to work with. For this presentation, I've created a simple single GPU example of a data science workflow using the Titanic survivors dataset available on Kaggle. When launching this container, I only allocated port 8888 because I won't need Dask in a single GPU case. Also, I mounted a volume containing the training data. After creating lists that describe the column names and the data types of those columns, I can use the read CSV function in cuDF to generate a GPU data frame. The next thing I do in this simple workflow is drop 4 variables from the original data set I don't think I'll need. Next, using the one-hot encoding function, I add some dummy variables to my data frame for gender and for the ports where passengers boarded the ship. Next, you can see I decided to fill missing values in the age and fare variables with the average value for each column. Finally, I split the data frame into 2 data frames and pass these both the XGBoost dmatrix constructor. Notice that dmatrix now accepts cuDF data frames natively. Here we see the hyperparameters I've chosen for this simple example. I want to point out these were not carefully chosen, and these are almost certainly not the optimal parameters for this problem. But as we can see from the in-sample AUC score at the bottom of the code snippet, the model isn't doing that badly for a first try. This is a subset of the hyperparameters that are available, and I'm going to describe a handful of them. Number of rounds determines the number of trees created for the ensemble. Max depth puts a limit on how deep the trees can grow. Tree method determines the tree construction algorithm. When working with Rapids, you almost always want to choose GPU hist, which we have done here. NGPUs, as you can see, is set to 1, which should hardly be surprising since I described this as a single GPU example. However, and this is important to remember, when working with Rapids, you will always want to set NGPUs to 1. This is due to the way that Dask works to distribute the workload across multiple GPUs, with 1 worker per GPU. We'll discuss Dask more when we get to the multi-GPU example. The objective function we choose is a GPU version of the logistic regression objective function. For a description of the other parameters I didn't describe, please see the XGBoost documentation. Now that we've seen a very simple example, let's move on to learning how to run the end-to-end workflow example notebook provided in the container. The example workflow provided is a prediction problem from finance. When a bank makes a mortgage loan in the United States, it almost always sells this loan to an investor. An investor buying a mortgage loan worries about two things. The first thing is that someone won't pay back the loan and they default on their mortgage. The second is that someone will pay off the loan very fast. When this happens, an investor is not able to earn the interest they thought they would be able to when they bought the loan. The end-to-ends notebook reads in data made available by Fannie Mae that follows a sample of mortgages over their lives. This publicly available data set contains information about the borrower's creditworthiness, various aspects about the mortgage, and data about how the mortgage performed over time. The data is in quarterly time frequencies. We have made the data available in various size data sets at the URL you see below. To run the demo, download a data set of an appropriate size for your particular hardware configuration. Once you have downloaded the data and launched the container with the volume containing the data mounted, some small changes need to be made to the Jupyter Notebook depending on your setup. The example notebook, as written, expects an 8 GPU node. In the example shown here, I'm running the notebook on a node with 4 GPUs. Because of this, I've had to modify the notebook where you see the arrow pointing in cell 2. The output below this cell shows 4 GPU workers successfully starting. In this slide, I'd like to draw your attention to the URLs reported in the output of cell 3. Here we see the Dask scheduler and the Dask dashboard have been started. Multi-GPU XGBoost with Rapids relies on Dask. Dask is a flexible library for parallel computing in Python. Dask is composed of a scheduler for optimized computing and collections that extend common interfaces to distributed environments. The Dask dashboard includes plots and tables with live updates. The dashboard includes numerous pages with information about task runtimes, communication, statistical profiling, load balancing, memory use, and much more. To access the Dask dashboard, point your browser to the IP address of the machine where Dask is running. Do not use the IP address that's displayed in the output cell. Finally, to run the demo, modify these data paths so they link to the volume that you mounted at startup. The last modification that you'll need to make will be to provide start year and end year values that match the data set that you downloaded. The part count parameter controls how many parts of the data you'll use in training the model. Often, the parts represent quarters, but some very large quarters have been split into smaller pieces to be able to be ingested by the GPU. Here you can see I'm only going to use 2 years of data and train the model on 8 parts of that data. This slide contains screenshots of the end-to-end notebook on the left and a page of the Dask dashboard on the right. This is an example of the E2E notebook being run on the 16 GPUs of a DGX2 and is intended to give you an idea about how you can monitor the progress of your workflow in real time. Some common issues with running the end-to-end example notebook are outlined below. By far, the most common error is running out of GPU memory. As a general rule of thumb for this particular data set, budget about 25% of GPU device memory to account for XGBoost overhead. The GPU overhead will vary due to a number of factors in other problems, including the sparsity of the data set and the particular data types involved. If you exceed available device resources, a Dask worker will crash. This error can be propagated forward in the Dask tasked graph and may result in very short ETL times. In some cases, errors of this type will lead to an error being raised by another routine referring to a none type. I will conclude by speaking briefly about how to set up multi-node, multi-GPU rapids in XGBoost. We first saw an example of this referenced on the slide comparing GPU-accelerated XGBoost to CPU XGBoost. Once you have successfully started your cluster, you can run the end-to-end example notebook on a larger subset of the mortgage data. On the Rapids GitHub page, under the Notebooks directory, there's a collection of utilities to make running multi-node XGBoost easier. Here you'll find the scripts and configuration file necessary to start your cluster. Dask.py launches a Dask cluster based on the configurations in dask.conf and by calling dasksetup.sh. The read-only file configures the cluster. It is read by daskcluster.py. The bash script launches Dask workers. It is called by daskcluster.py. The Python script is called by the user to launch the Dask cluster. Further details are available on GitHub. Now that we've discussed the utility files and changed the configuration so that it is appropriate to our given setup, all we have to do is call the scripts. Using Jupyter Cell Magic, run the Python script. The Python script uses a relative path to find the files. It should be launched in this directory, or you can change the script so that it has an absolute path. Finally, with this code, attach the client to the scheduler on master. Once you have completed this code, you can run your Jupyter Notebook on master like you normally would in the multi-GPU setup. Okay, well, thank you, everyone. Now we're going to take some of the questions that have been coming in over the course of the presentation. Once again, thank you, everybody, for joining today. We've already gotten some great questions from the listeners. The first questions I'm going to jump into are questions around hardware compatibility, and I'm going to scroll back to the requirements slide. So one question was, I have a mobile version of Quadro M1200 on my PC. Can I run Rapids? Unfortunately, because that is a Maxwell architecture, earlier than Pascal, that does not support Rapids. But we had questions about the Titan V or the GV100. Yes, Rapids will run well on that. The same is true of the Turing 2080 and 2070. We were asked about that. All of those can take advantage of Rapids. I'm going to move on to a question about XGBoost specifically. The question is, so the algorithm is mainly for solving classification problems. Well, I'll actually stop that question there and say that XGBoost can be used for both classification and regression problems. So going back to the slide of the successes that it had, the pricing question was continuous but truncated at 0 because it was predicting price. And the other examples are more classification heavy, but you can set up the XGBoost parameters when you run it to have a objective function that is for linear regression. Okay, it's great. We're getting a whole bunch more questions. So what other algorithms are supported by Rapids besides XGBoost? So currently right now in the QML package, we support principal components analysis, truncated singular value decomposition, dbScan, k-means, and k-nearest neighbors. And in the near future, we're going to be adding more and more algorithms to those. So for example, by the end of January, we'll have various flavors of linear regressions available. And it's an open source project, so we're also hoping that members of the community will begin contributing algorithms as well. Will Rapids and XGBoost take advantage of tensor cores? I don't believe that that's roadmapped right now, but you never know what the future holds. We're specifically focusing on, NV-linked architectures of multiple GPUs and multiple nodes of multiple GPUs for the time being. So thank you, everyone. I'm just going to take a moment to catch up on some of the questions that are coming in. Is it possible to know up front what is the potential boost performance before doing the migration or recoding? I mean, you can ballpark it. When we were originally building out the what became the mortgage example notebook that exists in the Docker container, we would do similar steps in pandas. And so, for example, in certain cases, reading in 4 quarters of data would take, a very, very long time. And using the CSV reader in QDF, it would be almost instantaneous. I mean, we're seeing very large speedups. I can't answer specifically for a given use case how great that would be, but another thing that was only touched on somewhat briefly in my presentation is that doing the really computationally intensive steps in data munging, such as doing merge and group by operations, that's something that's built into QDF. So workflows that involve a lot of that kind of data transformation, particularly compared to some of the other open source solutions for doing data munging, it's insanely faster. Okay, this is a question that asks, where can I find the demo notebooks? So if you navigate to rapids.ai, there's a link there that will take you to GitHub. It's also github.com/rapidsai. And at the very top of the page, there's a pinned repository containing our notebooks. Okay, sorry folks, I'm just catching up on questions really quick. Okay, here's another compatibility question. GTX 1080 is Pascal. Will Rapids run on a single GTX 1080? The answer is yes. As you start working around with Rapids, be mindful of some of the memory overhead, but that will work for you. Okay, sorry while I go silent. I know that they say that dead air is bad on these things, but I'm scrolling through the questions that are coming in, and I really appreciate how engaged everybody is. Is there a possible combination of DNN models in TensorFlow and ETL accelerated with Rapids? You know what, that's a great question. A member of our team recently just finished in the top 10 of a Kaggle competition called Plastics, I believe, that had to do with identifying astronomical data, and he used a combination of Rapids for the data munging, XGBoost, and then a model from TensorFlow. So for people that are doing more, neural net, deep learning kind of stuff, Rapids also presents a great way to cut down the time spent during your work that you're relying on certain solutions to get your data in the shape that you wanted. Okay, here's a question that says, if my code already works using pandas to store and manipulate data, is there a function that I can use to dump my data from a pandas array into a cuDF array, or do I need to rewrite my code using cuDF? There is a function in cuDF called from pandas, and it will transform your pandas data frame into a cuDF GPU data frame. And at the top of the getting started page for Rapid is a cheat sheet that you can download that goes over some of the commonly used functionality across data science and how it looks in cuDF. Will there be hyperparameter optimizers implemented in the future? So with the cuML package, the cuML package is built on individual, what we're calling machine learning primitives. And we're also continuing to work on expanding the collection of optimizers and other essential building blocks of various machine learning algorithms. Not only so that, we can continue to iterate on it, but to give people that, might know the math very well, but not necessarily the parallel programming aspects, the ability to compose algorithms from those primitives. In terms of Bayesian methods, it's something that we want to get to in the future, but it will actually be, I think, a little bit of time before we get into that. There's another question. Can Rapids be used for deep learning? And I answered this a little bit, but I want to emphasize again that the parts of your deep learning workflow that involve pre-processing and data cleaning and those kinds of, less glamorous aspects of deep learning can certainly be sped up by using Rapids. And within cuDF, there are I/O packages for outputting things in friendly ways to, for example, NumPy arrays to feed into different deep learning packages. How much recoding is required for existing models to migrate from CPUs and GPUs? So with the code base that ended up being the E2E notebook, part of it's going to depend on the size of your problem. There's a little bit of Dask code that needs to be added in a multi-GPU case. But if you have a problem that's doing an XGBoost, data set that's, we'll say, like 28 gigabytes, and you have or 26 gigabytes, and you have a 32 gigabyte GPU, you need to change a few of the XGBoost parameters. So, for example, you need to call out specifically like a GPU histogram and a GPU objective function. And there's very minor places where the cuDF API differs from the way that Pandas handles things, but it wouldn't be a substantial effort. It would be, substantially less effort than you can imagine moving from, like Python to R, for example, or from, R to PySpark or something like that. It'd be a much more easy transition with not particularly many lines of code. Okay, we got one question here that is, what is the pricing? The pricing is free. This is a open source package. It can be downloaded right now. The aspect where pricing comes in is how big of a collection of GPUs do you want to throw at your problem. But this code base itself is totally free. Will you be sharing this resource list and the presentation over email? I believe the presentation will be available after it is recorded. Many of the resources that were drawn into this presentation are on the rapids.ai page. It really is, can't be, oversell how, well the team is put together for such a young package doing such exciting stuff. Resources in one place that is easy to navigate for somebody introducing themselves to it. So there's some questions that I'm actually going to punt on and may follow up later. There's some people that are asking about the specifics about how the GPU makes XGBoost training faster. And it's a technical question about the sequential growth of trees during the boosting process. I will, try to follow up with a more explicit answer about that, but I don't think that we're going to address that today. Here's a question. Can we really force XGBoost to use a specific number of GPUs? Does it really work on Titan? I mean, like, the way that we've designed things, we can, scale up to a large number of nodes of multiple GPUs each. And part of that magic is done by Dask. This does work on Titan. Any Pascal or newer architecture, this is going to work on. Yes, we can scale XGBoost up to very large grids of GPUs. Here's a question about hyperparameter tuning. Do you have a function for hyperparameter tuning that runs on multiple GPUs under Rapids? So I know that adding an automatic cross-validation package to Rapids is going to be a very big help to researchers, but that's not something that we're committed to delivering right now. I will say when it comes to hyperparameter tuning, it is a lot less burdensome, even if you have to, manually tailor your cross-validation runs, doing it on, like any kind of rapid setup, really even like a single GPU setup. So the answer is that's something that we would like to do in the future, but as it is right now, hyperparameter tuning is certainly much faster using Rapids. Is Light GBM also supported? We are not currently supporting Light GBM. There is we also have, I think, on Arvix circulating a benchmark paper that shows that this, particular enhancement of XGBoost outperforms Light GBM. Okay, sorry, folks, scrolling through questions. Here's a question about, will there be geographic information system plugins or support for open source plugins in the future. As it is, the package right now is open source. One of the great boosters and early adopters of Rapids, who I only know through Twitter, is a man named John Murray that has done a lot of cool stuff with GIS data using Rapids already. The resource to find him is, I think it's at Murray Data on Twitter. But we're already getting a great amount of interest from the GIS community, and it's something that we would like to support more in the future. And we would also be delighted to see the community begin, letting us know what kind of enhancements that they need to do their day-to-day work. Can QDF QML run on large distributed data sets on HDFS? I know that we are working on making a HDFS connector, but it's not currently available at this time. But we certainly have future plans to support HDFS. Here's a specific question about XGBoost. What type of problems are better to use XGBoost on instead of deep neural networks? I covered this a little bit in one of my slides. I think that, so for example, I had previously worked in the financial sector, and in that sector, required by regulators to have models with recoverable parameters. You need to be able to say why the model made the specific decisions that it did. And in certain other applications, even if that isn't necessarily a hard regulatory requirement, in my work as a data scientist, in some applications, the interpretability of the model is important for getting stakeholder buy-in. Now, this is something that is, definitely experienced differently by different people on different problems in different workplaces. But I would also point to the contests that XGBoost has, continued to perform very strongly in, even with the kind of explosion in deep neural networks used in data science contests after we saw tools like PyTorch and TensorFlow become more widely adopted. I think it really comes down to the problem that you're trying to solve in particular, but XGBoost is quick, it's interpretable, and it does a pretty good job out of the box of making predictions. So I think it's well suited to, many problems that might not be ideal for deep neural networks. Do I have to run the provided Docker container on an Ubuntu machine only? Is there a version for Mac? Unfortunately, right now we are only providing support for Ubuntu, and I don't know that we have any plans to support a Mac version. But thank you for asking the question. Is support for R planned? This is an interesting question that's come up a couple of times. I think that in the long term, we would love to support R. I don't have any time frame at all for that. If people were, excited to jump in and see what they can do with R, I mentioned the ML primitives that exist in the QML library, and all the heavy lifting is being done by C and CUDA. So it would be a matter, I suppose, of writing the R wrappers around that. In terms of our particular roadmap, we don't have it on there, but it's something that I know that we'll want to do in the future. Okay, let's see. Here's a question that says, what resources would you suggest for Rapid's implementation with Google Cloud Platform? This isn't something I've done myself, but you know, it really depends on how many GPUs you want to spin up with whatever cloud service provider you're going to be experimenting with or using Rapids with, if you're doing it on a container in a public cloud infrastructure. I think that I think it's really cool to see the whole, you know, huge end-to-end workflow run on 16 GPUs. But I think it's also, you know, great if you're just getting started to spin up a instance that has a single GPU and just get a sense of how, for a lot of data science workloads that, you know, would take huge amounts of time in Python, are just so much faster when you are doing the same work, but you're doing it with Rapids on a GPU. Okay, sorry, I'm coming through. It's been great to have such a influx of questions. Has anyone connected this to Mathematica? I don't believe so, and that I don't believe there are any plans for. If you were really dedicated to using Mathematica, you could export the data in a trackable format that can be ingestible by Mathematica, and then, you know, do your work from there. I don't. The XGBoost, of course, if it exists in Mathematica, would be different. Okay, in case a long training job fails, are there checkpoints covering partial parts of the job on a rerun? That functionality we do not have at this time. These will generally fail very fast. So the risk that you have, that I've experienced in different things where you're running a job for a very long time and it fails 2/3 of the way through, and there's nothing to, or you can recover it based on certain software configurations. That's a lot less of a problem in Rapids because everything finishes so quickly. So we don't really have that functionality planned at this time. Okay. And I know that I have left some specific technical questions that came in unanswered. We will try to follow up with you after the presentation. How is this supported over Databricks and Cubole platform? I'm sorry if I said that wrong. I'm not familiar with the second platform. We're beginning to do some work with Spark, and so there'll be greater interoperability with, Spark in the next in the future. I guess this will be the last question I take. What's an example of an organization leveraging Rapids? One of our partners had a very, very large-scale problem that they were just not able to apply XGBoost to because it was too much of an engineering challenge to maintain a sufficiently large computing cluster. And by moving their workflow into Rapids, they were able to immediately realize, bottom line business benefit from making more precise forecasts at scale than they had been able to in the past. And I think that, that's the major value proposition with Rapids, is that you're able to get more out of your data scientists because there's less time spent waiting for algorithms to complete, and hyperparameter tuning is done much more effectively. And you're able to address problems that previously would have been intractable if you were going to solve them on CPUs. And so I think that's my favorite example of an organization leveraging Rapids. I think I have time for one more question, so please bear with me as I scroll through the list. Again, thank you to everybody that asked a question today and participated. We've all been really excited about Rapids and the possibilities as it opens up for data science, and you're excited too. Okay, here's the last question that I'll take. Any plans to incorporate this into scikit-learn? The approach that we're taking with scikit-learn is that we are going to be building out the functionality that exists in scikit-learn, but optimized to run on single, multi, or multi-node, multi-GPU installations. So in QML, we have a small collection of algorithms right now, but we are continuing to work on new additions to it every day. We would love to hear input from members of the community like yourself about what you use in scikit-learn to help us understand where our roadmap should be. You can do that by opening feature requests or issues in GitHub. Well, we are down to our last minute, and I hope that you all learned something today about what we're doing with Rapids and XGBoost on the GPU. Reach out to your NVIDIA team to learn more, or look for a follow-up email from us. Use the website. Go to nvidia.com/datascience and check out rapids.ai. Thank you all very much, and have a great rest of your week.